Today's discussion lecture 16 begins once again by our discussion on spectral analysis tool, and as we mentioned before that we would like to develop an analysis tool which is applicable for the full domain that would have different types of discretization for different points. So, in this context we have already discussed in last lecture about equivalent wave number. So, once we have developed equivalent wave number, we are going to talk about consistency of discretization in terms of this equivalent wave number expression. And once we apply it to specific space time dependent equation, we can talk about numerical amplification factor. We have seen already that Euler time discretization with various kinds of central schemes are unstable, and that is why we would move over to numerical amplification factor for 4-stage Runge-Kutta method, because we have already talked about the requirement of single step method as opposed to multi-step methods. Once we have talked about space and time discretization together, we are in a position to talk about numerical dispersion relation. Once we have the numerical dispersion relation, we will show how phase speed and group velocity could be computed from this numerical dispersion relation. This we will do it specifically with the help of 1D convection equation, and we will show the power of this analysis tool by comparing different finite difference, finite volume and finite element methods one by one. And we would like to bring one particular aspect of any discrete computing method is the existence of spurious upstream propagating solution, and this is what have been called as Q waves. So, this is something we will be talking here in great detail. This would basically conclude our discussion on discretization. So, having finished our discussion on discretization, we will basically start our discussion on various solution methods. So, we will begin by solving parabolic partial differential equation, and in this context we will adopt the heat equation as an example of parabolic PDE. So, we will begin our discussion of parabolic PDE solution method by theoretically analyzing the heat equation. Specifically, we would like to bring to your attention the concept of physical instability versus numerical instability. That is why we need to have a firmer understanding of theoretical aspect of the solution, and in this context we may like to introduce an equivalent energy, and having done that, we will show that for a physically stable system we cannot afford to accept numerical instability. And in the context of this, we are going to also talk about consistency and accuracy of solution methods for PDEs. Then we should continue with our discussion. We are actually in the process of developing a analysis tool which is in the spectral plane. That is why we call this as a spectral analysis tool, and what we have been able to do is also analyze such a scheme in the full domain. That means unlike what people have done earlier, people have developed methods where you could just simply look at the scheme what happens in the interior. But as you can notice here that we can find out the effectiveness of discretization in terms of this k equivalent in a node wise manner. So, for each and every j, I could evaluate this the moment I decide to freeze upon the method of discretization through the choice of the C matrix here, right. And on the blackboard we did develop this, right. We showed that if we take a second order central differencing scheme, that gives k equivalent as sin k h by h, and then from there actually we drew a portrait of this effectiveness and plotted it in the non-dimensional wave number ranging between 0 and pi, and on this side we plotted k equivalent by k, and what we noticed that k h going to 0, what we are getting here k equivalent by k here would be sin k h by k h. So, that is your sin x by x, and we know the familiar property of the function that it just simply decays to 0 like this, and this is your value 1. So, ideally what you would like to have is that all scales are resolved exactly, but discrete method shows that it is scale dependent. Depending on the value of k, you have different effectiveness. What about this point? This point has to be equal to 1. Why? Because this is the limit for which you are going from the discrete to continuum, h going to 0, right. If h goes to 0, then we reach this point, and then of course, my equivalent resolution should be exactly equal to the theoretical estimate, right. So, that is something that we have talked about. Now, suppose you take care of this discretization of the first derivative in that convection equation. So, basically investigating this simple equation, and we have seen what the second order discretization does. So, suppose you do it by fourth order central differencing scheme, that I think you would recall this was the expression that we had written, u j plus 2 plus 8 u j plus 1 minus 8 u j minus 1 plus u j minus 2. Sorry. So, once again we can calculate its k equivalent. You can very clearly tell me what this is going to be. K equivalent would be 1 over 12 h, and from here I will get e to the power 2 I k h, right. So, I will get minus e to the power 2 I k h. From here I will get 8 e to the power I k h, and from here we will have e to the power minus I k h, and the last one will contribute e to the power minus 2 I k h. So, you can see things do happen pairwise. So, you have here appear with the opposite signs. So, you could club them together, each one of them will contribute 2. So, we could take this quantity out. So, this will be nothing but I could also take I out. So, I will get here sin 2 k h from this and that, and from there we will get 8 sin k h, right. So, this is the expression for k equivalent, I k equivalent. So, of course, you can write k equivalent by omitting that 1, sorry, that I. So, you will get that, and do a little bit of simplification, and you will get this expression. So, what you find that the fourth order differencing is equivalent to the second order differencing quantity multiplied by this factor, and this factor has a role to scale it up. What I mean by that is, if this is the figure that I have gotten for CD 2, for CD 4 I will get something like this, right. So, all that it says that I have a much larger range of k h over which my representation is more accurate, right. So, this is the story with all explicit method. As you keep on increasing its order, you keep seeing that this gives you better and better approximation. However, for all the cases you would notice that this will go to 0 at the Nyquist limit. Yes. Pardon? Here plus, and that is why this has given us this, right. Maybe I should have a minus sign here, right. So, I should have a minus sign there too, right. So, so this is the story when it comes to discretization. So, what we are looking at here is what happens when we just discretize the spatial derivative term alone. Now, the story does not end there, because what you end up doing is solving a particular equation where both space and time dependence come into play. So, if I look at this equation, and in this equation what we are going to do is again represent the unknown in terms of Fourier Laplace transform. So, I will write like what I did yesterday, u of k and t and e to the power I k x dk. So, that is the way that we are going to look at it. So, as you can see, then this term will give you an integral du dt, and of course, this term remains as it is, okay. And this term will give us c by this is a lowercase c. So, I will write it like this, and what did we write this as in terms of, if I am doing it for let us say the jth point. So, I will write it c j l e to the power I k x l minus x j, right, and L goes from 1 to n, and this multiplied by u, and of course, the phase path remains as it is. So, basically this is what we are getting from here to here via this spectral representation. Now, of course, if it is true for the integrated quantity, so the integrand itself must be equal to 0, and that is what you have it here. The top equation is essentially this. Essentially what we have done, remove the phase part, remove the integral part, and what I have here is this. So, I have du dt plus c by h, and the C matrix operating on the projection operator times u, and so a little bit of a manipulation will get you in this figure form. Now, in most of your computational activities, wherever convection is involved, you will always notice appearance of this parameter, which is shown here in that square bracket. This is a non-dimensional quantity. Okay. This is what is called as the Courant-Friedrich-Lewy number or CFL number. So, just simply remember it as a CFL number. What it basically tells you is a kind of a non-dimensional quantity n c, which we will write, and we will see that this is a fundamental independent variable that determines the property of the method. Now, having defined the variable in terms of its Fourier Laplace transform like this, we can define what we will call it as an amplification factor. This will define it as u for that particular k where we are looking at the solution at the advanced time step divided by the solution in the k space at the old time step. So, in a sense this is going to be a function of k. You can very clearly see that in the limit of continuum, when we take delta x equal to 0, delta t equal to 0, this g should be equal to 1. It is easily seen, right? If delta t goes to 0, this limit goes to 1. What happens is a different story. We do a finite time step calculations, and the moment we do that, we deviate from its ideal value of 1. Okay? So, in computation, always, irrespective of equation, you will always expect g should be as close to 1 as possible. What does this mean? Look, if I have g greater than 1, what does it imply? It implies the solution is growing with time. Okay? So, that I will call it as instability. So, since this is an action of a numerical activity, so I will call it as numerical instability. If g is equal to 1, then it is neither growing nor decaying, and I will call that as neutral stability. And this case, when g is less than 1, we call this as numerical stability. So, with time, the Fourier Laplace amplitude will keep decaying. Please do understand, there seems to be a lot of misconception among the practitioners of computing in the CFD community. I have noticed time and again, people tend to always think that you must have a stable algorithm. Nothing can be far from truth. As you can see from the definition here, g should be equal to 1, and it does not matter what equation you are looking at. When I come to discussing parabolic partial differential equation, I will specifically pose a physical problem, and I will talk about its physical instability and then relate that with the numerics. However, irrespective of any equation that we are looking at, this is what we want. We should always aim for neutral stability. That is our ideal limit. Okay? Please do download this paper. This will have all these discussions given a little more in detail there. So, what happens is, once I have written it down like this, now suppose I perform a Euler time integration. So far we have been silent about what we are doing with the time integration. So, let us say I am performing a Euler time integration on this term. So, what I would do, I would write it as u of k t plus delta t minus u of k and t divided by delta t, right. Then of course, you can see this is the outcome, because there is a u sitting out there. So, I could pull it out and I get du by u equal to minus of this n c times this summation over this factor. What happens as a consequence? Of course, if I divide by u, so this divided by u of k and t will give me g. So, g minus 1 will be equal to this factor. So, G will be equal to 1 minus N C into this factor. What does it tell us? I have been telling you for a long time that this is a potentially a bad method to do Euler time integration. Why? You see, the C matrix is going to be of real entries. The way we discretize, you have noted various methods, some of them you have seen. C is a real matrix, but this phase function is complex, right. So, what we can do is, I can take a modulus of this G, and immediately you will notice that this is greater than 1, right. All of you see that. So, this modulus of this G is greater than 1. What does that mean? That is a unconditionally unstable method, right. So, you look worried. Tell me, you have any confusion? Yeah, let's work it out. So, I have 1 minus N C and this C J L, and this will be cosine k x L minus x j, right, plus I sin k x L minus x L minus x j. Right, you can see this. So, you have you can see the real part 1 minus N C and you have the imaginary part, which will be nothing but now, can you see what I said? Okay. So, you are now convinced that of course, this modulus will be greater than 1, and that makes Euler time integration very undesirable, very undesirable. It will lead to instability. Okay. So, this is that. So, what are the other better methods that we have? And let me tell you, for some of the time integration methods that we have investigated, we have developed ourselves, we find this is a prime candidate which gives excellent property, and this is your 4-stage 2-time level Runge-Kutta method. Okay. So, let me explain how this method works and how this method is better in terms of numerical amplification factor. Supposedly, I have a space-time dependent equation. So, I do all kinds of spatial discretization, put all those terms on the left and right hand side and call it as a L operator. Okay. So, that determines all your spatial dependence. And then we have this kind of a evolution equation del u del t. Well, please forgive me, this should be a lowercase u, this is not that capital U, it should be lowercase u. So, del u del t is equal to L of u, and by now all of you are familiar. We have already done it when we are looking at solution of ODEs, that in the 4-stage Runge-Kutta method we perform these 4 stages. Having started with the solution at the nth level, we find out a intermediate stage solution which we call as u superscript 1. Having obtained that, use that to calculate this function L of u here, and then from there we calculate the second stage function u2, then we have the u3, and finally, we collate all these intermediate stages into the next step solution, that is u n plus 1. This is all there in your notes. So, in fact, you can notice that one of the bracket has gone wrong up in the stage 2. Anyway, 2 and 3 there is something wrong. Okay. So, basically then let us see what happens when we incorporate our spectral description and try to get the value of g for this particular time integration method. So, coming back to your 1D convection equation here, I can put this on the left hand side, right, and if I do this, so this quantity is nothing but your L of u, right, that is your L of u for this scheme. Now, we have also said that the numerical description of the derivative with respect to x, we could write it like this. So, if I write delta t times there is a c out there and times del u del x, we are going to get this, right. C is there, delta t comes from when I multiply, as you can see in the previous stage, every stage I need to multiply by delta t here, right. So, here you can see there is a delta t by 2, delta t by 2 and so on and so forth. So, delta t is part of the story, and so we get once again that factor C delta t by h, that is what we call as the CFL number or NC, right. So, that C delta t by h, we keep it up front here as NC. Then of course, this is what we have done. This PJL is nothing but this quantity e to the power I k x l minus x j. I have just simply economized on space by writing that, and then of course, you have to have the Fourier Laplace amplitude u k of t and integrate over all possible k's, that is what you get. So, again let us economize in expression and call this whole thing here N c times this summation C j l P j l. Let me call that as A of j. What does the subscript j imply? The j implies that we are looking at the phenomena at the jth node, right. So, that is what we are doing. So, having done that, this is our first stage, u of 1 is obtained in terms of the starting gate point u n times this path, right, that is what we have to do, and that happens to be minus A j by 2 and this quantity. So, u n itself is u k t n e to the power I k x j. So, the whole thing can be written like this. So, I could write u of 1 as some kind of a Fourier amplitude u of capital U of 1. That capital U of 1 is nothing but u k evaluated at t n times this 1 minus A j by 2. So, this is the way that I will describe the first intermediate solution, either in terms of 10 or in terms of its Fourier amplitude by this expression 11. Now, go to the next step. The next step follows in a similar manner, because what we do there, we take u n minus delta t by 2 into L of u evaluated at the previous intermediate stage u of 1. So, that is why what I could do is I could write it in terms of its Fourier amplitude u of capital U of 1, and again this gives me capital U, this quantity, but u of 1 we have already written down as u into 1 minus A j by 2, but there is this upfront factor A j by 2. So, that comes in here. So, the whole thing works out like u of k comma t n 1 minus A j by 2 into 1 minus A j by 2, right. So, basically then this whole quantity minus this phase path is the Fourier amplitude for the second intermediate solution, right. And we proceed and obtain the third quantity, the third intermediate stage, that is u n minus, again this is delta t. See, in u 1 and u 2 we have delta t by 2, u 3 we have delta t. So, that is why we have just A j, otherwise previously you are getting A j by 2. So, u 3 is u of n minus A j into u of 2 into this, and u of 2 is right in front of you, plug it in there, this is what you get. So, that explains to you what this u of 3 is, right. So, this is an expression that helps you explain everything in the k plane. Now, having obtained all these quantities u1, u2, u3 etcetera, you put it in the final correlative stage where you get the solution at the new level in terms of the older value, and this is what you get. Do a little bit of algebra and you get this. So, we get 1 minus a j plus a j square by 2 and so on. So, what we get here for this RK4 method is this, and as you can see this a j itself was a function of n c and those p j l etcetera. So, that brings in the non-dimensional wave number here k h and n c. So, this g j is going to be a function of k h and n c. But please do remember that a j's themselves are complex. So, g j also will be complex, and what it does, this sort of operation with g j will not only amplify or attenuate, but it also will provide you with a phase shift, right, is not it. So, if I have a real quantity and an imaginary quantity, I can write it in terms of a modulus times e to the power I phase, right. So, basically every operation, every time step would be equivalent to multiplying the previous time step solution with the amplitude plus a phase shift, right. Now, you would be interested to know that what kind of a phase shift that you are getting, because in solving this equation that we have started with, namely the 1D convection equation, the solution is very straightforward. The solution is, as if you recall, we would write it like this. If I write in terms of, not in terms of k and t, but let us say now in terms of the frequency itself, if I introduce frequency, then what will happen? Then I will have e to the power I k x minus omega t, okay, and dk d omega. So, that is what I will get. And you can see the phase path. The phase path is I k x minus omega t. So, if I take k out, I will get x minus c t, right. So, your actual solution shows the phase to change by this expression x minus c t. If I give you a solution at t equal to 0, at a subsequent time you have the same solution, but it is shifted by c t to the right, x minus c t. So, this is your a kind of a phase shift. Okay. Now, I want to know that this g that we have uncovered here for this RK4 method in 17, what does it do? How is it related to the c that we are looking for in the exact solution? To understand this, I have demonstrated here what happens. Suppose I start from the initial solution, which is given by the initial spectrum a naught of k times e to the power I k x d k, and then I am looking for the solution at the first time step delta t, and that I will call it u of 1. Please do not confuse it with the first stage of RK4. This is what I am talking about, time integration going from u 0 to u delta t. So, this is your u delta t. That would be equivalent to multiplying by g of k. That is the definition of our amplification factor. Now, this g of k itself, as I have written here in terms of a modulus and times a phase shift. And what is this phase shift? It is nothing but tan inverse of g imaginary by g real with a minus sign up front. So, what happens is I could then write this u, the solution at delta t would be the initial spectrum times the modulus of the amplification and e to the power I k x minus beta j. Why do I write j? Because each and every point will have a different phase shift. That is what we have developed through this matrix theory, that we can obtain this point wise. So, that is what we conclude here, that every step of time integration shifts the phase of the solution obtained at the previous step by this amount minus beta j. One needs to ensure that this phase shift is according to the exact solution. We need to do that. So, suppose I perform n such steps. So, I have arrived at the solution at the nth time step, that would be again given by my initial spectrum. There is a mistake, this g j of k, there should be a power n, because every time I get 1. So, if I am doing n steps, so there is a n missing here. Please do understand that there is a mistake. Please do not quote me later that your note was wrong and that is why we have done it wrong. So, what I am saying that you will have g j of k, this has been operated n times. So, this is an exponent, right, this is not a superscript, and then I have the phase E k. So, if I am doing this and every step I am getting beta j, so I am going to get minus beta j, right, this times decay. Okay. So, there is this n missing. So, please do note there correctly, this is incorrectly written. Okay. Then what happens? Now, having obtained this expression, you notice, compare this with this here. If I look at this phase relationship with this phase relationship, I can see something emerging, that this beta j is somewhat related to this omega here, right. What is n? N is nothing but the time step. So, that will be like your T n by say let us say delta t, right. So, what happens then? N times beta j, that what we are seeing here, that is going to give me something like this, IKCT, right. So, I will write that as, there is a I here also, sorry. So, n beta j should be equal to then to k c t if everything was fine and nice. However, we have already seen doing discrete computation means sacrificing something, and what is that something? K is still our independent variable. So, we are keeping that as our point of reference. What we are going to see, that this c, which was to be a constant in the exact solution, numerically it does not remain so, right, it does not remain so. So, if I replace this n by what I have written there, t by delta t, then you can see, of course, this t will cancel, and what we are finding here then, an expression for C n, that is nothing but beta j by k delta t. Right. Okay. From the exact solution, we have noted omega equal to k c, right. So, this is our exact solution, but numerically what we are doing, k still is the independent variable, c does not remain the same, this also. Okay. So, this is your what should I call it? This is our numerical dispersion relation. See, we are relating omega with k. That's what we define. At this stage, it may appear it's a very simple thing. Tell you what, that people have been doing things wrongly for decades, including us, as you can see here. It started with Professor Tefatan's work in 1982, then Lele, Colonius, ourselves, and this is Professor Ishwaran from Mechanical who copied our work wrongly, and that's what they also ended up doing wrongly. So, what you understand here is that your independent variable is k. What was the mistake people were doing wrongly before? You know what people were doing wrongly before? They were just simply writing omega n as what we have done in the beginning of the class, change k to k equivalent and then say multiply by c. So, this is wrong, whereas this is the correct way of expressing the dispersion relation. What does it mean? I mean, are we just simply nitpicking? No, it is very profound, because what we are seeing here is that this C n is now a function of k, whereas in your exact solution C was a constant. That is why we talked about so glowingly about it, that it is a non-dispersive, non-dissipative solution. And here what we are seeing, the very act of discrete computing, we are getting a numerical phase speed C n, which is a function of wave number. So, that means what? Different k component will send their crest at different rates. So, this is really a big development which was first pointed out here. Well, we have tried to convince people with a host of publications there, as you have noticed. Continuing with the discussion that C n is not equal to C is really profound in terms of error and stability analysis. There is a nice history about this. When during the Second World War, this group of people were in the Manhattan Project in New Mexico developing the atom bomb, one of their main stalwart mathematicians helping them was von Neumann. And von Neumann actually developed a error analysis or stability analysis, and this was based on this assumption, the wrong one. And at that time, of course, during the war, people are secretive about what goes on in research front. They classified the work. So, people did not know what was the work, but everybody knew that von Neumann has done something which revolutionizes computing, explains a lot of features of computing. So, it was only I think in 1947 and 49 some papers started coming out, but as you can realize that that work was wrong, and we actually first brought it out and we corrected von Neumann's error. That is the main thing about this work. What we notice out of all this exercise, that I have gotten an expression for C n. So, what I could do, I could define a non-dimensional quantity, which I will call it C n by C, and so that would be beta j, and I will have k c into delta t, and k c is omega, right. So, beta j by omega delta t. So, that is what we have written here in 21. So, this is your consequence of numerical activity, that you do not see C n by C equal to 1, but it becomes beta j by omega delta t. So, what happens? So, you choose a method for spatial discretization. you choose a method for temporal discretization. You obtain the value of g, right, which has a real path, which has an imaginary path. You find out what is the imposed phase shift from this g, and that determines how far it is from 1. And of course, having given you this expression here, you can immediately calculate the numerical group velocity, which I will call it as V g n, which will be nothing but d omega n dk. Right. So, if I plug that in there, I will get this equal to C n plus k d C n dk. Right. If everything was nice and fine, you should have seen that this two should have been the same, right, V g equal to C, that is the exact solution. But the very fact that numerical calculation makes C n non-constant function of k adds on this part. That is the source of numerical dispersion. In fact, lot of calculation goes on in the literature, where people do claim that they have done this and that. They are essentially source of this spurious dispersion that is inherent with all numerical methods. You cannot just simply wish them away until and unless you choose your methods and parameter very, very carefully, and that also tells you that at this point in time, with the type of computing power that we have, we cannot solve the equation in a direct sense. We will always have to live with some kind of error. What is the error? How this error is contributed? As we go along, we will explain more. At this point in time, I will show you some results. Well, this figure may not make tremendous sense, except that this figure. What we have done, we have plotted this g contours, the modulus g that we have talked about, and the method in the second figure that we have, it is a CD2 method along with RK4. We have marked the region here with a dashed line where your g is mod g is 1. Recall, I wrote down that to do a correct calculation, we must have neutral stability. So, this have been plotted in this plane. On the x axis, I have NC, the CFL number. On the y axis, I have KH. What it tells you that to do a error free calculation coming from numerical amplification consideration, you need to keep your delta t very small, that means NC very small, so that you remain in the numerically neutrally stable region. Well, there are other methods. I will talk about these methods, but just simply know that this is a finite volume method, this is a finite element method, and unfortunately, neither of these two methods, which are very popular, very much in use, maybe tens of thousands of people use them, but as you can see, they do not have any g equal to 1 region. So, all they get is lot of well, you have solutions here. This is g equal to 1 line here. On this side, you have totally damped solution. So, as you keep integrating, your solution amplitude will come down. Okay. On this side, you have unstable path, this pocket. The same thing happens here with this finite element method called Petrov-Galerkin method. Some of you may have taken a course, you know what it is. What you notice that g equal to 1 line is here. On this side, it is a completely damped solution, and on this side you have amplified solution. So, this is about the story of g. You need to also know what is the numerical dispersion. We have talked about this, right, V g n by C. So, if we plot that again in NC and KH plane, we notice some very interesting feature. Let us keep our attention focused once again on this second figure, because that is what we are quite familiar with now. what we notice that that V g n by C, this contour line, I suppose this line is 0.98. So, basically even if you let us say look at very small range of k h here, you are already started getting 2% dispersion. Instead of 1, it is 0.98. This line here corresponds to 0.98. But interestingly enough, look at this line. That is a very fascinating and interesting line. That is V g n by C equal to 0. What does it mean? That below that line you have V g n by C positive, above it is negative, and the equation that we started solving, solution should have propagated from left to right if C is positive, right. It goes from left to right. But if my numerical dispersion relation is such and I am in this part, solution will go in the wrong direction. This feature is vaguely understood, but this is where we have actually quantified it and put them across for different types of methods currently in use. This is one of the methods that we have developed. You can see that this value is actually pi by 2. So, for any k h value which is greater than pi by 2, they will go in the wrong direction. And since these are not physical waves, so somehow this nomenclature has stuck. This type of spurious solutions are called not p waves, but q waves. Okay. So, q waves means spurious upstream propagating solutions. Okay. As you can see, almost every numerical method has this kind of a feature. So, you cannot just simply say that I have one method superior to other. In fact, the case for finite volume and finite element is really pathetic, because they not only attenuate the solution, their dispersion relation property is also equally bad. So, I think we would conclude here. I still have not told you about the error analysis part, which will come little later. You please download this paper and then I will come back to there shortly, but let me now go to the next topic that we would like to discuss. That is basically going back to classical thing that any computing course tries to teach you, how to solve different types of PDEs. So, let us begin with parabolic PDEs, because that is how historically it all had begun. Well, once again with our formal practice, we start with some given equation. So, let us look at say one dimensional heat equation, right, in a domain, finite domain, x varying between 0 and 1, and for all time we want to get the solution. Of course, it is a space time dependent solution. So, you require a initial solution here that is given by this function f of x, and in addition it is a bounded domain problem between 0 and 1. So, you need to prescribe boundary conditions, and the boundary conditions of course could be time dependent, right. So, that is why we have written them as p of t and q of t. Now, we have already studied it, we know it, that the characteristic is t equal to constant, right. That is how the information propagates. Now, we would like to first discuss what is the property of the physical solution itself for very large time, because if I do not know that, then I do not know what I am computing. So, first and foremost I would like to know what the solution is doing, and to understand that we define a quantity, a non-negative functional, which I christen it as energy. So, let us call this capital E of t as u square dx. So, this is a positive function. We want to find out how this quantity changes with time. So, what you do is you have the definition, differentiate it with respect to time, then you will get u del u del t. Del u del t is u x x. So, I have got this, then I can do it a little jugglery here, and that is what I am going to get del del x of u x minus u x square. So, if I do that, this is exact differential. So, I can integrate it out, and with the help of those boundary conditions at x equal to 1 and x equal to 0, the first part gives me these two solutions, right. Whereas, the last part I keep it as it is, that is minus of u x square this. Now, many a times, most of the time when you are taught in this any of these equations, especially the heat equation, you are most of the time are told, well, let us look at something, we give some initial temperature distribution and then see what happens. So, there is nothing from the boundary. So, if I do that, this P and T, P of T and Q of T are 0, then this part is not there. Then what happens? I have d dt is equal to minus of this. So, it is a strictly negative quantity. So, what does it say? That if I do not do anything through the boundary, then the energy is going to decay with time. So, that is a very nice feature of a physical solution. We do not like to consider a physical case where energy grows unbounded. There would be such problems of physical instability, but that is not what we are talking about. Here we are talking about a benign case where solutions do not blow up. What it shows that if I have a rod, I create some kind of a heat distribution at T equal to 0, what happens subsequently? It says, while you look at the solution, the energy will continuously keep coming down. However, you can realize by a judicious choice of this function P and T and Q and T, we can do a lot of interesting things. So, in the second part, I will show you some interesting things that we have done very recently to show you that even for this parabolic equation, heat equation, you can actually generate wave solutions. We will do that, but that is for later. So, we have come to realize that when we do not have any boundary excitation, the energy of the system decays with time. So, it is basically a physically stable system, then one should be able to compute it indefinitely. So, there should not be any problem until unless your method is wrong. Okay? If your energy increases with time, then of course, we have physically unstable system. You cannot compute it. You will see that other physical processes will intervene, and you will never get a situation where solution goes unbounded, because somewhere the energy has to come, and various processes like what we studied in case of soliton, you realized that there was this competition between dissipation, this focusing and dispersion that got us a steady state solution. So, literally speaking, in physics you will never come across a continuously unstable system. It will be unstable, but then it eventually saturates because of other processes. However, coming to our numerical stability requirement, we need the energy of the physical system to remain bounded. Not only that, we also need these two quantities, which of course would make sense. We need the solution to be accurate, and we need the method to be consistent. See, we have defined something like this: the energy is going to decay with time. I will introduce you to a method which was introduced with a lot of fanfare, and people actually used for nearly 30-40 years. Even you can go to the search engine and find out there are still some people using it. There is this method called Dufault-Frankel method. What it happens that it does not follow the principle of the physical solution. So, such methods are called inconsistent methods. So, we must keep concerned about consistency. Okay. So, I think it is a nice place to stop here.